Good morning, Mr. Lisham is here. Let me sort out this camera. Oopsie. And we are carrying on with our investigation of cubic functions. What we're doing now, we are drawing more cubic functions, but ones that have one stationary point or even no stationary point. So the last lesson, we sketched a cubic function that had two stationary points. And we already spoke about the possibility that some cubic function might have just one stationary point or perhaps even no stationary point. So those two are the ones that we're going to deal with today. And to do that, I'm going to teach you a little trick. Okay? And the trick is to think about a mother function, which is f of x equal x cubed. Let me just close the door. Some more quiet. So f of x equal x cubed. Now I claim that it looks exactly like that, and I'm not going to prove that it exactly looks like that, but what I'm going to prove that it only has one stationary point, okay, which is in the origin. Now to do that, we use the simple, the good old-fashioned way. We find the derivative, which is 3x squared, sorry. And to flush out these stationary points, we must say, okay, I'm looking for the place where that first derivative is equal to 0. So I need to solve the equation 3x squared equal to 0. That obviously only have one solution. You can say two solutions, plus minus 0, but obviously that's the same thing. So there's only one stationary point. Okay? Now if there is one stationary point, okay, that means that you don't have another hump. It's not going up and then down. There's no two stationary points, just one stationary point. Then if you think about it, that stationary point is also a point of inflection. I mean, you can look at it from this picture here. You can see that here we have concave down, here we have concave up. So this origin is a stationary point. The first derivative is 0. And it's also a point of inflection. Now you're not going to be requested to prove it, but it's actually very easy. How do I prove it? I find the second derivative. Okay? If I find the second derivative, it is 6x. And if I sub x equals 0 here, I'm going to get 0, which I know is our condition, necessary condition for point of inflection. So I can erase this now because all you need to remember, okay, that the mother graph f of x equal x cubed looks like that. It has a stationary point, I'll call it SP, stationary point, and a point of inflection over here in 0, 0. Okay, let's move on. Okay, now, how do I move on from there? What I can do to this graph to generalize it, okay, I can basically move it to anywhere here. I can move it to the right, I can move it to the left, I can move it up, I can move it down. Okay, we've done a lot of that last year. And we're doing it with what we call a vertical shift and a horizontal shift. So if for example, okay, we'll take numbers. I'll use the numbers that I'm going to use in a second. If I turn this into f of x equal to x plus 2 cubed minus 1, what I essentially did, I moved the whole graph, shifted it down by 1, that's a vertical shift, and the plus 2, if you remember with the horizontal shift it's kind of in reverse, I shifted 2 units to the left, okay? So this graph is shifted down and to the left, okay? More generally, if I take f of x equal to x plus p cubed plus a q, then what I've done here, I've shifted it by q, up or down, depends. Q positive it's up, q down is negative, the q negative is down. And I shifted it, horizontal shift by p. Now I can add one more parameter, and that's the a, okay? The a doesn't change this stationary point, but it can stretch the graph. It's a stretch factor, if you remember. We said that's a vertical shift, that's a horizontal shift, and that's a stretch factor, okay? Okay, we will add something to that in a second, but let's go back to our specific example. What my aim is, what I'm trying to do is sketch this graph. Okay? Now, how do we sketch all our cubic function last lesson? We found the first derivative. We made it equal to 0. And that's going to give us our stationary point. Okay? Then we found the second derivative, made it equal to 0 to find the point of inflection. Then we found the x-intercept and the y-intercept. Okay? What I'm saying is that I actually don't need to do it. Okay? I mean, I could try and find out the first derivative, but it actually will be really, really, not very difficult, but as it is now, I can't find the first derivative because I don't know how to do the derivative of this thing. It's not actually a very difficult thing, but it uses something called the train rule, which you don't need to know in high school. So if you wanted to know what the first derivative is, okay, first of all, you have to open it. And to open a cube is not too difficult, but it takes a while. It's very boring. So no need to do it. What you can figure out is, look, I know what the stationary point here. The stationary point here is 0, 0, right? Stationary point here was 0, 0. And I know we already said that this graph is basically the same as this graph, same shape, okay? It's just shifted 1 down and 2 to the left. So let's draw that. We'll draw it in red, okay? So that means that this stationary point went 1, everything, the whole graph went 1 down and 2 to the left. That means the stationary point as well. It went 1 down and 2 to the left. So the stationary point now is going to be at minus 2, minus 1. That's the new stationary point. And I'm just going to draw it and just make sure I do it right. Okay? So the graph, the new graph is going to look like that. Okay? So here's the new graph. That's the graph f of x equal x plus 2 cubed minus 1. The point of inflection, which I must note, I always write, it's a point of inflection and a stationary point, is minus 2 minus 1. And I need to find out these two intercepts. Okay? Now, to find this intercept, okay, that's very easy, right? Because I just put x equal to 0. So if I put x equals 0, 0 plus 2 is 2, 2 cubed is 8, 8 minus 1 is 7. So this point is 0, 7. To find out the x-intercept, a little bit difficult. Well, not too difficult. We basically say that y is equal to 0. So I'm going to write y equal to 0, x plus 2 cubed minus 1. So I need to solve this. Now, there's two ways of doing it. One the long way and one is much quicker. If you want to go the long way, again, you have to open this cube. And that's going to take a while, okay, to open, because we don't really have a formula for a brackets cube. We have to open, first of all, do a square and then time by x plus 2. Okay, so instead, let's move the 1 to the other side. I'm going to write x plus 2 cubed equal 1. And how do I get rid of this cubic root? You guessed right. I'm going to cube root it. Okay? The cube root of 1 is just 1. So I'm going to have x plus 2 equal 1 or x equal minus 1. Okay? So the x-intercept is minus 1. Okay? The red graph is the 1. I'll just pause here for questions. Cool. Now, I think I just need to do one little kind of final rule here. If you ever come across a function, a cubic function that look like that, and you want to draw it, just remember that your mother graph is that blue graph. Okay? Obviously, if a is positive, it's going to be that shape. If a is negative, then it's going to be the opposite shape. It's going to be like this. Okay? And your P and the Q will tell you where is the stationary point of point of inflection. So stationary, I'll write it down here so I can read. I'll put SP and POI, it's the same point. Okay? Where are they? Let's think about that. Plus Q, that means, just a second guys, no, wait for me. Okay? So the plus Q means this whole thing moved up. Okay? So the point of inflection, the y value is going to be plus Q. The x value, this thing shifted to the left. You know, if P is positive, it's shifted to the left. If P is negative, it's shifted to the right. So the new x will be minus P. That's going to be the point of inflection and a slash stationary point. Okay, I'll pause here for a second. Okay, so that was for a specific class of function, cubic function, that can be written like that. So we learned a little shortcut. We don't actually have to find the first derivative and all. We just use this, okay? If you get a cubic function that doesn't look like that, then we can't do the shortcut. So again, we're going to find a stationary point, point of inflection, y-intercept, x-intercept. To find a stationary point, okay, we find the derivative, it's minus 3x squared plus 6x minus 3. Okay? To flush out the stationary point, you must say, okay, then that must be equal to 0. And that's the equation we have to solve. Okay, to solve that, I'll divide by minus 3. I'll get x squared minus 2x plus 1 equal to 0. Okay, you can use your calculator to solve that, you can use a formula, but you know, the best thing to me is just to be able to realize, to factorize it. It's x minus 1 squared equal to 0. So you know, normally most quadratic equations there will be x minus 1 times x plus 3, whatever, then you'll have two roots. But this, when it's the bracket repeats itself, then we say that there's two roots, but the roots repeat itself. It's the same one. So really there's only one solution, x equal 1. So again, even though this equation doesn't look like anything like that, right, it still have only one stationary point. And that point is x equal 1. Now we're going to carry on. I'm not going to do the whole thing, I'll just go through it. Okay, so we found, I'll draw it here, we know that x equal 1, okay, we have a stationary point. Also by looking at the minus here, the one in front of the x cube, we know that this is going to be a graph that looks like this. It goes down. Okay? We got to find the y. How do we find the y? We just substitute x equal 1 here. And I'll do lots of shortcuts here. I'm going to get the answer y is equal 8. So I'm going to have a point 1, 8. Okay? The point 1, 8 is my stationary point slash point of inflection. Okay? Because that's the situation when I have one stationary point. The stationary point is also the point of inflection. And the graph would look something like this. Okay? Alright, now all I'm going to do is just find the intercept. And I'm not going to show you how to do it. You guys know how to do it. In fact, to find the y-intercept, you don't even need to do anything. You just need to look at the equation. Okay? Obviously, you sub x equals 0. You straight away see that the answer is going to be 9. So that's the y-intercept. To find the x-intercept, a little bit more difficult. We got to write down, okay, maybe I will go over that. You're going to say, okay, all this thing is equal to 0. So minus x cubed plus 3x squared minus 3x plus 9 equal to 0. Now, how do I solve such a thing? Okay? Now, to solve such a thing, if you really want to be clever, you need to be able to factorize it. But we're not trying to do, we're not heroes. We just feed it into the calculator. Okay? We showed you how to do that. And straight away the calculator will tell you there's only one solution here, and that's x equal 3. Okay? So that's my y-intercept, and that's it, I'm done. Okay? Let's move on. Okay, so we've covered two stationary points. That was in our last lesson. And in this lesson so far, we looked at a couple of examples. We have just one stationary point. Now the next function, g of x, you can probably, if I ask you how many stationary points it's going to have, you're probably going to guess that it's going to be 0. Not that you can recognize that this has no stationary point, but because we covered all the rest. Okay? So how do we actually find out that it only has 0, so there is no stationary point? What we're going to do is we find the first derivative. As always, to flush out the stationary point, we find this first derivative. Okay, minus 3x squared plus 6x minus 9. And we make it equal to, correct, to 0. Right, and now we try to solve it. So the first step, you can factorize a minus 3 and divide it. So in other words, divide by minus 3. So it's going to be x squared minus 2x plus 3. Now you can try and think, can I factorize this? I need to look for two numbers that add to minus 2 and multiply to 3. It's not going to happen. It's just not going to happen. If I get a negative number here and a positive number here, they both have to be negative. Okay? But so that means minus 3 times minus 1. That's the only way I can multiply two negative numbers to get 3. But minus 3 minus 1 is minus 4. It's not minus 2. So then the other option, maybe you couldn't find the answer, you try the formula. So you're right, x equal minus, remember that formula, x equal minus, okay, I'll write minus b plus minus square root b squared minus 4ac divided by 2a. In other words, equal to minus b, that means minus minus 2 is plus minus b squared, that would be 4 minus 4a times 3. Okay? And all that divided by 2. So what we get is 2 plus minus. What is 4 minus 4 times 3? It's 4 minus 12. It's minus 8. And my friends, we're in trouble. We're in trouble because we have a negative number under the roots. Okay, that's what we used to call the delta. This thing is the delta. And if you remember, we had a lesson way back last year. If I have positive delta, we have 2 roots. Okay. If delta is 0, I only have 1 root or repeating roots. And if delta is negative, no roots. That means no solutions for this equation. Okay? And if there's no solutions for this equation, we have to understand what it means. Okay, we've got to ask, okay, what do we try and find out? We try to find out for which x's will be the stationary points. And if the answer is no solution, that means there's no stationary points. So this graph, okay, is going to look either like this or like this, okay, with no stationary point. By recognizing that this is minus, then I know it's going to be one of those. Okay, so there's no stationary point, but there is a point of inflection. I can find a point of inflection. Okay, so it's not going to be a stationary point, but it's a point of inflection. I always have to have one point of inflection in a cubic function. I have to. Yeah, I might not have a stationary point, but I will have a point of inflection. How do I find a point of inflection? Yeah. Well, the first derivatives allow us to find out, to flush out all these stationary points. It's the second derivative that allows us to find the point of inflection. So I'm going to do derivative of that. I'm going to get minus 6x plus 6. And to find these point of inflection, I must make that equal to 0. And very quick, you can recognize that x equal 1 solve this equation. In other words, x equal 1 is a point of inflection. Okay, to find the y, I'm just going to sub 1 here. And I'll do it a little bit quick for us. Y equal minus 7. You sub 1 here, you'll get minus 7. So the point 1 minus 7, okay, that point is a point of inflection. Okay, 1 minus 7. Okay, now as we said, the graph is going to look like this because this is negative. So I'm just going to draw it. Okay. Oh, before I draw it, okay, well, I'll start drawing it. It's going to be drawn like this. Okay. And the question is, where is it going to cross the x or the y axis? In other words, we need to find an intercept. So to do that, I'm just going to erase this there. To find the intercept, let's start by always find out the y-intercept first, because it's very easy. I just sub x equal to 0. If I sub x equal to 0, 0, 0, 0, well, I'm getting 0. So what do you know? 0, 0 is my y-intercept. But if it's my y-intercept, it's also the x-intercept. In other words, this graph crosses here. Okay? And that's what it looks like. I recognize that I have a 0, 0 and the point of inflection. Now, just a point here before I finish. You got to be careful the way you draw the graph. This is a graph with a point of inflection which is not a stationary point. And the two graphs we drew before, we drew graphs that were point of inflection that were also stationary point. And you got to make sure that the examiner can see that that's what you mean. What is the difference between these two? If I was to draw a tangent, and again, not that you need to draw a tangent, don't draw a tangent. But I, as an examiner, need to be able to see that the graph here is horizontal. If I draw a tangent here, the graph here is not horizontal. Again, the reason is this is the point of inflection, which is also a stationary point. Gradient is 0, first derivative is 0. And this is a point of inflection, which is not a stationary point. The derivative is not 0. Okay, take care, bye-bye.